Swayam Prabha. Digital India. Educated India.
Let's say we have created good enough physical media and we are able to send data from one point to the other. But when you are trying to create a cluster, it is not point to point, as I mentioned previously, right? So you need to connect it to some element. So on top of the physical layer, now comes the network layer and routing. Okay? So before we get into the network layer, we need to look at a switching element. I'm giving an example of an InfiniBand switch because I come from NVIDIA. We use InfiniBand. We also use many other kind of interconnects like NVLink. Industry uses many different kind of interconnects as well, but this is one of the most popular interconnect for HPC systems. InfiniBand constitutes around 90% of top ranking systems, right? What is this switch? Well, it's actually a silicon device which has multiple ports, as you can see on the front panel. On these ports, you connect the physical media that I talked about. You connect a copper cable or an optical transceiver. Okay? The transceiver or the copper cable is receiving data from one server. The data comes in at a very high rate. We are looking at this one is, let's say, 200 gigabits per second. The data comes in, and now the silicon needs to decide what to do with the data. So obviously it contains some sort of header. Header contains the source destination, the source address, and the destination address. So the silicon inside this switch is required to look at the destination, and then it is required to check from which port it should send that data out so that it will reach its destination. For doing all these checks, it needs to have some sort of a table inside. Okay, so that and the table needs to know to reach a certain endpoint what port I should use. This is where the concept of switching and routing comes into picture. And the time taken for this silicon or the time taken for this ASIC inside the switch to take a packet in, decide where to send it out, and to send it out is the latency between its two ports. And this is again one of the most important parameters for high performance network. When we talk about latencies in today's terms, it is of the order of 130 nanoseconds for this particular switch. That means one data byte coming in or a packet coming in from port number one after 130 nanoseconds will appear outside a destination port. Okay, so but to do that, first we need to create a network, right? So what do we do? So if you need to create a cluster, okay, a small cluster, you will take multiple servers and you will, let's say, connect it all to that particular switch. The switch, as you saw on the previous diagram, contained around 40 ports. So data, it can actually connect 40 different compute elements together, and it can form a single cluster. When you want to make a larger cluster, you need to, how do you do it? Either you can increase the size of the switch, or you can try to connect multiple switches together to create a particular topology. Now, obviously, the limitation of what size a switch you can make, you would see there are large switches as well. If people are from the Ethernet world, you will see there are switches which contain 1000 port or 500 ports or 40 ports or 100 ports. Even in InfiniBand, there are switches which contain 1600 ports. But this is not a single switch. It is actually a big device which contains multiple ASICs inside, and they are connected to each other in a certain way. A single ASIC, there is limit to how big an ASIC you can make. One of the simplest limit is the die size. You take a large wafer, and to get good amount of yield, you will have certain size of die on it. A certain size of die will be able to service only certain amount of ports, because finally you need to take electrical signals out of that die. How many ports you can take out of that die would depend on how many pins or ball grid arrays you will have from that silicon. It's a very simple way of saying that, okay, I cannot take a 2-inch by 2-inch die, because then my yield is not very high. So we always, industry always tries to do the best price performance, and based on that, the largest radix, or I would say the largest port count network processor that you see today is of the order of maybe 40 ports or 128 ports, ranging between that, right? And obviously, you know that there are clusters which contain thousands of compute elements. So if a single chip has got only 40 ports, how will you make thousands of compute elements? So how will you connect thousands of compute elements? You start making these topologies. Okay, now topologies in a high performance computing cluster cannot be random. Why? So the whole World Wide Web, the whole internet is a particular topology, right? Every endpoint is connected to every endpoint through some link. But the way I'm presenting over here right now, my computer is connected to my service provider, to my society's fiber box, from there to my service provider's distributed unit, from there to a core switch, from there to one of the major routers or the gateways in India, in Mumbai maybe, from where there are some inter-sea cables, it goes somewhere. So Ethernet, World Wide Web, it's a connection of all these elements, and you have a standard protocol running through all this. In an HPC cluster, you cannot do just random connections. Why? Because the aim is different. The aim is that all compute elements, it's a democracy, all compute elements have same kind of capability. They have, therefore they should have same kind of network bandwidth and latencies and delays. Therefore you need to connect them in a well defined manner. And because and one of the another reason that you need to connect them in a well defined manner is because, and we'll come to that, is because you need to get them to talk to each other uh, in a in a symmetric way, right? And therefore we create, I will not go into the loops, let me go forward. So you create a certain network topology which is defined by equations. Therefore you can have equation defined routing to be done between these elements. There are various kind of network topologies. We look at standard tree topologies, fat trees, hypercubes, toruses, dragonfly. What is common between all these, and what is the difference between this and a World Wide Web mesh, random mesh? The difference is that all of these topologies are very nicely mathematically defined. Therefore, you can define routing between all the elements which constitute this particular network. And this is where the network layer, the link layer and the network layer comes into picture. Uh, these are some examples of topologies. If you want to make large clusters, you will end up putting multiple of these switches. You'll connect uh, them to each other in a particular fashion. You'll create multiple layers, and therefore you can create very large clusters. I'm talking about a normal 3-level class topology, because let's say if you you took only two switch, the maximum compute that you could connect is equal to the number of ports of these two switches minus the number of ports which are required to connect the two switches together. So if it was a 40 port switch, maybe you could connect 30 servers to switch 1, 30 servers to switch 2, and there were 10 links between the two switches. If you want to grow more, you could create a triangular or ring network. If you want to grow more, you start making these kind of trees, okay? Or you start making these kind of toruses. Here every box represents a switching element. Every arrow represents the link between the switching element, okay? And then you keep on folding these connections, and you create a very nice, well defined, mathematically explained topology. Therefore you can actually put this equation into the routing engine of the switching element there, which will now know where to send the incoming packet if it has a certain destination address. High performance network need this deterministic routing, and there are now adaptive routing as well, which we'll cover in the next session, next part of this presentation. But the bottom line and the takeaway is, to create a high performance cluster, you need the network to be well defined so that the routing elements are they contain routing tables which are given by an equation so that they can send out packets without any issues or without any delays. Okay. More than that, you always want, whenever we are creating clusters, we always want there should not be any packet drop. In Ethernet, we are allowed packet drops, right? Why? Because, well, it connects to the entire World Wide Web, and there can be congestion if it is not 100% reliable thing. If there are problems in the middle, you can drop packets, and then the software can request for retransmission. In HPC, if you have the software trying to request for retransmission, the whole process will become so slow that you cannot actually scale your application. So you need to have a routing which is credits based, as in every element knows that it has got a path available to its endpoint, and therefore every source can send data to the destination without dropping packets. uh, if you just now look at, now let's go one step back, so let's complete the link layer and the network layer portion. So as I said, we are sending zeros and ones. Zeros and ones are bytes which are put into packetized formats from the server. The packet contains maybe some a delimiter to basically tell the server that, okay, one packet is coming, send it out. It will contain a local routing header, a global routing header, some transport header. It's a standard OSI 7-layer model, which is actually the basis for most of the network. Actually, I would say all of the network. Okay, so there will be some identifier which says where is my from where I'm coming. The main payload is this in the center, but there are bytes which define, hey, from where this payload is coming, for where this payload is intended to go, at least this much is needed, right? And then what kind of operation is it? So all this comes inside the packet format, comes into the network layer and the transport layer. Okay, so we covered till physical layer, link layer, and networking layer. Let's go into the transport side. Right? Transport layer is the entity which defines, for high performance computing cluster, it defines so for normal normal Ethernet, there is sockets, like there's a sockets interface. If you try to send data between two servers, you send it through sockets. In high performance clusters, you don't open sockets. If you open sockets and you put data into that, it needs to be processed by the kernel and the driver. Okay? So actually, if you look at it, on the bottom side, on the top side is what happens in a typical TCP/IP protocol. The application, which is a routine, let's say it's a routine which contains data in a particular buffer, and that buffer is part of the, obviously, the RAM. Okay, the application copies that buffer to the sockets layer, that copies the data from its own buffer to the transport and protocol driver inside the adapter in a server. The adapter breaks it down into, in Ethernet we call it MTU, right? So it has to break it down into a particular transfer unit, and then it will send it out through the physical adapter, through the cable that we talked about, or through the interconnect media. There can be switches in between and connected to various topologies. The job of the switch is to look at the source and destination and route it accordingly. We are assuming that it has routed it correctly and it has reached the destination. That in the destination, again, there will be multiple copies of that data between various portions in the buffer, and the data will reach the target. This whole cycle of copying data from server to a client, or server number one to server number two, is the latency. Let's say I wanted to send only one floating point in number a double precision 14-point number from server number 1 to server number 2, in today's world, we take around a microsecond. Okay. In TCP/IP based connection, we take around 10 microsecond. Why do we take 10 microsecond? Because of these so many buffer copies are involved. Therefore, for high performance network, you need to have the transport layer which kind of bypasses all these intermediaries. It bypasses the entire kernel driver and protocol driver and buffer copies and so on and so forth. And which is where an example like InfiniBand, which does something called remote direct memory access, RDMA operation, where it can actually read data from buffer of one application, which is in the RAM of one application, and put it across to the memory or in the RAM of the second application. Because it is able to do that, the latencies are of the order of some microseconds, or actually some hundreds of nanoseconds in today's world. If you take two servers, okay, let me come into real world, right? Today's world right now. If you take two servers, GPU enabled or not, connected with a wire through an InfiniBand adapter or any high performance network adapter, and you try to do a ping pong between the two servers by exchanging maybe few bytes, okay, you will be able to do it in around 600 to 700 nanoseconds, because we bypass all these points. Okay. Now comes another important concept of having accelerated computing. We all have been doing these sessions for GPU accelerated computing. I'm sure you've gone through sessions where people talked about GPU acceleration, CUDA programming, and kind of offloading parallel workload onto the GPUs and so on. When you do that, and as long as things are confined within a single GPU, it's fine. But now when you want to create a cluster of GPUs, again you need to transfer data from one GPU to the other. So currently, if you look at how systems are made, you would have a CPU. You just open a, if you look at a motherboard of a standard server, you will see a CPU, you will see a chipset, some PCI Express switch on it on the motherboard. The CPU will have the DRAMs, which are the memory. It will also contain a GPU. Okay? The GPU will have its own GPU memory, its own RAM. When you are trying to accelerate a workload onto a GPU, you will actually copy the operands from the CPU memory onto the GPU memory. And the GPU will then do some matrix vector multiplication, matrix multiplication. And then after certain iterations, if it needs some newer operands, it will write down the result onto the CPU memory, get some new operands. Okay? All this communication is done from the CPU and the RAM through the chipset to the GPU memory. What if we wanted to send data across two servers containing GPUs? Let's say my matrix was quite big and I want to send from memory of GPU number 1 to memory of GPU number 2, which is a different server. So now I need to copy my data because I'm able to do DMA operation from only the system RAM. We weren't sending data from GPU or memory from system number 1 to memory of system number 2. Okay? When you want to do that, you can only address the memory which is in the system, which is the RAM. When you want to send data from GPU memory, you will need to copy the contents of the GPU memory into the system RAM, into the area which is addressable by the GPU. And then there needs to be a memory copy done between the area which is addressable by the GPU and the RAM area which is addressable by the network card. You need to do that copy. And then the network card can do a DMA operation, which I explained in the previous slide. What we did was, rather than doing this memory copy, okay, we worked with systems where we worked on chipsets and technologies where we said, okay, let's have a unified memory in the system RAM, which is addressable simultaneously by the GPU as well as the adapter. Obviously, there are lock mechanisms implemented in the control plane so that you don't end up corrupting the memory. But once GPU has written its data onto the system RAM, the adapter can access the same area in the system RAM and do a DMA operation to the other side. And therefore, it gives a good amount of acceleration, because now you have completely avoided the memory copy within the system RAM. We went one step ahead and said, hey, if I have to exchange data from one GPU's memory to the other GPU memory, why should I even copy it into the CPU memory? Why can't I have my network card directly access the GPU memory, and therefore save up all the cycles of sending data from GPU memory to CPU memory? And this was also done. So these technologies in the transport layer, these are all part of the transport layer. Okay, these technologies in the transport layer of network are called RDMA, GPU direct RDMA, GPU RDMA sync, and so on and so forth, fancy words. But all they do is, in that packet that I showed in the previous slide, apart from the source and destination identifier address, it contains a transport header, which is nothing but a DMA pointer to the memory location of the destination where the payload needs to be put. On reception of that packet, an intelligent adapter makes sense out of the transport header and puts the data directly into the GPU memory. And therefore now you can get huge amount of bandwidth gains without using any of the CPU cycles, and huge amount of latency gains as well. So whenever you hear the word GPU RDMA or RDMA, this is the technology that people are referring to. There are, I talked about, like, there needs to be a control plane which ensures that data corruption doesn't happen when 2-3 devices are simultaneously accessing, or when to packetize and what to send. So there is a control plane. Earlier the control plane was actually controlled by the CPU. So, and only the data plane was accelerated. Now with the latest technology that you will see in the GPU clusters that you are actually being exposed to, even the control plane is running inside the GPU in sync with the adapter. So there is no involvement at all of the CPU for the GPU to GPU communication, and therefore we end up making a very, very efficient GPU accelerated cluster of multiple hundreds and thousands of nodes, which we will talk about in the coming slides. Okay, so just to conclude this part of the presentation, I think we are 5 minutes over. Just to conclude this part of the presentation, we talked about the fundamentals, we talked about latencies, we talked about bandwidth, we talked about what are the limits to this bandwidth. So let me just give a quick picture of latency. Why are we doing this RDMA, GPU RDMA? Because we want to have as low latency as possible between all communicating compute elements, whether be it accelerated computes with GPU or standard x86 CPU or ARM CPUs, right? We want to reduce the latency. Latency is a combination of all these factors. It is a combination of the cables which are there in the network. It is a combination of the switch and the topology. I'm showing here a big switch which contains multiple individual switches in a particular topology. It is a combination of how fast the network adapter on the endpoint is able to look at the packet and do a DMA operation. And eventually, what a programmer sees is the MPI latency, the message passing latency, or the communication framework latency. In when you take the example of the communication libraries for maybe a TensorFlow or a PyTorch, right? So just to summarize, the latency of the media is actually 4 to 5 nanosecond per meter, and it's a hard limit. Why? Speed of light. Okay? Light travels at a certain rate, 3 lakh kilometers a second, which corresponds to certain nanoseconds per meter. In a media, the speed of light, or the speed of the electromagnetic wave, is defined by the speed of light divided by the refractive index if it is a optical media, or divided by the permittivity if it is a standard dielectric media, which corresponds to usually 5 nanosecond per meter. It's physics, you can't change it. So if you have a very large cluster, okay, people sometimes ask me very naively that, okay, why can't I have a very large supercomputing cluster by combining all the computers in a city? You can do that. You can run problems which are embarrassingly parallel, which you can divide amongst all the compute elements, and they don't need to talk to each other so frequently. You can do that and you say, okay, I've got a big system. But when you're looking at scientific applications and we are looking at coupled applications, you need to talk very fast. Okay? And that's where, if you make clusters which are very large, you actually keep on adding latencies. When you look at optical cables, you add some more latency for the electro-optical and opto-electrical conversion back. When you make a large cluster, you will have to have multiple of these switching elements, as we talked about. The switching elements have certain amount of latencies between them. I said 100 nanosecond, 130 nanoseconds, right? Then there is this transport layer, which presents a latency of around 600 odd nanoseconds. Again, I'm showing the numbers just to give you a practical whiff. I'm showing you the numbers which are there for a high performance interconnect like InfiniBand. The highlighted numbers are what you see in a standard network like Ethernet. Okay? Again, physics does not differentiate between a high performance network or Ethernet or whatever. So the latency of the media is the same for both the protocols, but the other latencies starts differing. Why? Because if you take a switch, Ethernet has a protocol which is designed for the World Wide Web. So it contains a lot of complexities in its headers. It contains a lot of things like, you have IP addresses, you have, protocol port numbers, and you have so many quality of service things, VLANing, whatever, right? Because that's how Ethernet was designed. Therefore, when an Ethernet switch receives a packet, to take a decision, the time it takes to make a decision of where to send depends on the complexity of all the headers. In a high performance network, you're not connecting it to World Wide Web. It is for a very fast set of computers within a data center. And therefore, you can do away with the complexities of all the other headers. And therefore, the switch can take a decision very fast. And therefore, the switch has very low latency. Okay? TCP, since you're allowed to drop packets, you don't do a DMA operation. You have 7,000 nanoseconds of latency when you want to do a single byte transfer from one computer to the other. Whereas high performance networks, RDMA enabled networks, are 1/10 of that. So with this slide, I'm just showing the differences between, if somebody says, okay, what is the difference between a standard Ethernet with that RJ45 versus a supercomputer that is in CDAC? Let's say, some Param Siddhi or Param Yuva that is in CDAC. Well, it contains right up from the hardware to the networking equipment to the software. It contains elements which are highly tuned and designed for high performance clustering and communication. Okay? So with that, I will stop here, and then